Okay, go ahead and respond to the online poll for attendance if you have not done so already, and we'll get started. How's everybody doing? Good, sort of. It's week 6. Can you believe it? I know. I feel the same way. So we've got how many? 6, 7, 8, 9, 10 in finals. I guess 6 weeks. Yeah, less than 6 weeks, and some of you will we'll all be done for the year, but some of you will be done with your college education forever, possibly. And then some of you will come back for next year or for grad school or whatever. But anyway, it's so crazy. Okay. Anyway. Happy Monday, week 6. Here we go. All right, so yeah, I got sick last week, and so I didn't get to say everything I wanted to say about, and I still have to update my drafts and whatever. But we'll just have 2 weeks, 2 lectures in week 5, and that'll be what I'll say about kind of the, what was it? Maximum likelihood estimation models of stuff. There's a little bit more that I might have said. You can go through the textbook, but I will not test you on anything that I haven't at least touched upon in the lectures. So we'll just keep moving along, just so we can kind of keep on pace with the I guess the content that we need to cover in the course. And so so we're going to move right along into classification. Okay. So if you have the textbook, we spent a lot of time in chapter 1, and then we spent, I guess, week 5, like kind of touching on chapter 2, and then I'm skipping chapters 3 and 4 entirely. 3 and 4 cover Bayesian statistics and Bayesian methodologies, and that's something that we cover in 102C. If you've already taken that, or if you're going to take that, we'll cover Bayesian methods and Monte Carlo methods, which are very closely related. So I'm skipping those things, and we're going to move right along into chapter 5, which is on classification. And our first classification model or method is the Bayes classifier, and that's what today's topic will be. So this is where we are. We're chapter 5 in our textbook. And the classification problem looks something like this. You've got, in your training data, you've got n observations, and we're assuming these are kind of multi-dimensional observations. So each one's a vector, okay, of dimension d. And each observation has an associated class label, okay, because this is a classification problem, so they belong to category A, category B, category C, right? So it's kind of like in your homework, the flowers were either Setosa, versicolor, or virginica, or something like that, okay? And so you've got these classification labels, and and we label them, like 1, 2, 3, okay, up through letter C. And it's important to note that we treat these as class or category labels. So even though you might have class label 2 and class label 1, you can't treat class label 2 as being twice as big as class 1 or something like that, right? And it's also not meaningful to have a label like 2.5 because this is not some continuous scale. They are class labels, okay? And anyway, the goal is that we get some kind of new object in our test case, which is going to be our x observations x new, and for that case we want to predict the class label t sub new. Okay, so this is just the classification problem, and we kind of touched upon it with the neural networks homework, but I guess today we'll look at kind of the Bayes classifier. Okay, and so the Bayes classifier will use Bayes' rule to find the probability that some observation belongs to some kind of class, right? And it's a probabilistic classifier, which means it's going to return probabilities, something like it belongs to class A with 19% probability, and it's class B with 80% probability, and it's class C with 1% probability, okay? So these are different probabilities, they add up to 1, and that's what we have. And I think you guys do logistic regression in 100C, is that right? Or 100A? 101. 101C, okay. All right. In one of your classes, you do logistic regression. Okay, I'll fix this. 101C. 101A. All right. Somewhere along, it should have been covered, right? And logistic regression is a dichotomous classification model, meaning it's going to classify as either 0 or 1, and you've got this logistic curve. And anyway, that's what you get, right? Okay, so we're not going to cover that. Have you guys already done the Bayes classifier somewhere else? Okay, good. So it's good that I'm doing this, right? Okay, and then we have non-probabilistic classifiers, which we'll talk about later, which use kind of like these quote hard rules, and they designate classes without an associated probability. So it's just going to say, you know, the observation 1 belongs to class B. End of story. Okay. And those would be things like k-nearest neighbors or support vector machines and stuff. And and this is also important to note. The Bayes classifier is an application of Bayes' rule, but it's not considered to be Bayesian statistics. Okay, so Bayesian statistics we kind of cover in 102C, and the big idea there is you treat your unknown parameters as random variables rather than fixed values. But today we're going to just treat them as fixed values. But we use Bayes' rules, so this is the Bayes classifier. Okay. All right, so Bayes' rule, Bayes' theorem states this, right? The probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Okay, so this is what we have. And so the numerator, probability of B given A times the probability of A, that's just equivalent to the probability of B and A, or A and B. So this should all have been what, 100A? This is your probability rules and all of that, right? Okay, and then the denominator, we can kind of decompose the probability of B into kind of, we can partition it, and we can say it's the probability of B and A plus the probability of B and not A, okay? And these things are mutually exclusive, so you can just add them together. And if you take B and A plus B and not A, it's going to cover all possibilities of B, right? And so the denominator, one thing you can note is that it's equal to the sum of the numerator across all possible values of A. So A can either be A or not A, and if you take the numerator where it's A, you're going to get the probability of B and A. And then if you take the numerator where A is the opposite, its complement, you know, you're going to get the probability of B and not A, all right? And so the probability of B is just the numerator across all possible values of A. Okay, well, so that comes in handy later. And so when we do the Bayes classifier, this is what we want. We want the probability that some new observation, okay, where we've got the values in the input vector x new, what's the probability that this new observation belongs to class C, whether that's class 1 or class 2 or class 3 or class A, B, or C, or whatever it is, you know, class versicolor or setosa or virginica. We want to know what's the probability that this observation belongs to this class, okay? And so we're going to express it like this. It's the probability that T new, being the class label T new, is equal to some label C given the input values, okay, the values in the input vector x new for this observation, plus all the values in the training data x and all the values, all the labels in the training data t. Okay, so this is what we want, right? And we're basically going to just apply Bayes' rule here. Okay, so this is the part we want, the A given B. Okay, this we can kind of think of this as the probability of A given B, and we're just going to kind of use Bayes' rule, and we're going to say what's the probability of A given B is B probability of B given A times the probability of A divided by the probability of B. So so we're going to just apply Bayes' rule, and but before we do that, just keep in mind this is still a probability, so all of your probability rules apply, meaning that this thing has to be between 0 and 1. And then if we look at the probabilities of all possible classes, they have to add up to 1, right? So if there's 5 classes possible, when you calculate the probability that this new observation belongs to class 1 or class 2 or class 3, 4, or 5, those things have to add up to 1 because it has to be one of those 5 classes. So the sum of these probabilities have to add up to 1. And I think, this example, I've got 19, 80, and 1%, and that adds up to 100%. Okay, so when we use Bayes' rule, okay, this is what we get, right? So we've got kind of the t new given x new, and this is going to be the probability of x new given t new is equal to c, multiplied by the probability of t new is equal to c, divided by the probability of x new. Okay, so this is kind of like your A given B becomes B given A times the probability of A divided by the probability of B. Okay, and I've labeled these posterior, likelihood, prior, and marginal, which are all kind of terms that get used frequently in Bayesian statistics, but again, this is not a Bayesian statistics method. We are using Bayes' rule, and so kind of these labels still stick around, but it's not a Bayesian statistics method. So anyway, the posterior, this is the thing that we want, the probability that our new observation belongs to label C, or class C, okay? The likelihood, this part, the x new, probability of x new given t new, this is the probability of observing the data that we have in the vector x new, okay? So this is kind of our test case. We've got the measurements, and based on these measurements, we want to predict the class. And so this is the probability of getting these measurements if we assume the new observation belongs to this specific class C. Excuse me. I should have brought some water. And then this xt appears in everything because all of these probabilities are based on the training data x and t. The prior, this part, is a probability that some new observation belongs to class C before we know anything else about it, okay? And again, these things are based on the training data x and t. And then finally, in the denominator, probability x new is the probability of observing the values in our input vector x new, regardless of the class label. All right, and again, all of that is based on our training data x and t. So that's why x and t appear as givens in all parts, because everything we have here is based on the training data. So we can take advantage of the fact that all of these probabilities add up to 1. You get bonus points here. Thank you so much. This is a friend indeed. Thank you. All right. So we can take advantage of the fact that this stuff, the results, have to add up to 1, right? And so if we've got like 3 different class labels, these resulting probabilities have to add up to 1, which means this denominator part is just going to be the sum of the numerators, right? So if you figure out the numerators, and the numerator is like 5 and 6 and 7 or whatever it is, okay? We know that the denominator, in order for everything to add up to 1, is just going to be the sum of the different numerators, okay? And so that's what we've done here is I've just expanded the probability of x nu to be the sum of the numerator across all possible classes. And this looks a lot scarier than it is, but it's just take the numerator, set it equal to class 1, calculate it, and then do the same for class 2, class 3, all C classes, and then add them up. Okay, so I think we're going to just move on and do a silly and simple example. It's really contrived, but this is the best example that my brain could think of, and my brain can only think of pouches with red and blue marbles. So so this is what we've got. All right. So this time you decide to purchase a bunch of these pouches, okay, and they're all filled with red and blue marbles, and you order these from some, I don't know, some arbitrary company online, right? And then and when they arrive, we find out that the pouches are filled at 3 different factories. Okay, we got factory A, B, and C, and each of these factories, somehow we know that they just have different proportions of filling the red and blue marbles. Okay, and so in our shipment we get 25, and 24 of them are labeled. Okay, 12 are from factory A, 6 are from factory B, and 6 are from factory C. And then the last one is not labeled, and this is going to be our test case that we're going to try to kind of guess which factory that it came from, okay? And we're going to assume that when the pouches get filled with marbles, that it's some kind of Bernoulli or binomial process, okay? That it's they're just randomly drawing red and blue marbles, and it fills the pouches, okay? So this is what we're going to assume, all right? And here's our training data. I found this thing of a bunch of pouches, all right? And then we got our one test case, all right? And so these are all labeled A, B, or C, okay? Half of them are A, and 6 are B, and 6 are C, and based on that, okay? And then so we go through all of our training data, and we're just going to summarize our training data with these summary statistics, okay? So for these 12 pouches that came from factory A, after tallying everything up, 60% of the marbles are red, 40% are blue. Okay, for the ones from factory B, half are red, half are blue, and for the ones that came from factory C, 40% are red and 60% are blue. Okay, now, so there's a few things to keep in mind. We don't work at the factory, so we don't know the exact filling proportions as far as like what proportion exactly is red and blue. And then the pouches themselves exhibit variation, but it's not enough to kind of cause us concern about our assumption that it's a Bernoulli or binomial process, okay? So, I said, for example, one pouch from factory A had 14 red, so it has a proportion of 70%, while another one had 11 red, 55% or something. And so this is just kind of part of the natural variation of some kind of Bernoulli process where the true proportion is 60% red, right? So we're going to just kind of assume that we've got this binomial distribution filling up our stuff, okay? And these summary stats are just going to be the maximum likelihood estimates of the kind of filling proportions based on the data we've observed. So so basically, we just basically dumped out all the bags and we counted them up and we get a maximum likelihood estimate, right? I mean, we could do something different, but I think just to kind of keep things simple and straightforward, we're going to just use the maximum likelihood estimates based on what we've seen. Okay, and so now now we have our test case, the 25th bag, and we want to know, before we even open it and look at the data inside, look at what the proportion of marbles inside are, we can ask, what is the probability that it comes from a particular factory, right? And so here, the prior probability is a probability that this new observation comes from some particular class before we know anything else about it, right? And so based on our training data, it seems reasonable to assume that it comes from factory A with probability 0.5 because 12 out of the 24 bags were from factory A, right? And so if we apply this kind of reasoning to our full data set, we would say it comes from factory A with probability 0.5, comes from factory B with probability 0.25, and factory C with probability 0.25, okay? So kind of in formula form, it looks like this, all right? 0.5, 0.25, 0.25, given our training data. So right now we're just kind of assuming that, because half of the bags in our order that were labeled came from factory A, we're going to just assume that this has a probability of 0.5 from coming from factory A, all right? Does that feel okay? All right, so, and now we're going to calculate the likelihood, all right? So we open up the bag, we dump out the contents, all right? And there's 20 marbles, and 10 of them are red, okay? So we have P equal to 0.5, and we want to know which factory produced this bag, right? So we're going to calculate the likelihood. Okay, so if you just hear that the proportion in our bag is 0.5, based on this, what do you think? It seems like B, because fills with 0.5, but also factory A fills it with 0.6 and factory B fills it with 0.4, so it's possible that it comes from either of those as well, right? If factory A fills with 0.6, it's possible that it makes a bag where only half are red, okay? And if factory C fills bags with proportion 0.4, it's also possible that you get a bag where half are red, okay? So any of these things are possible, and we're going to calculate the likelihoods, right? And so, we use the binomial probability, and we do n choose x, p to the x, 1 minus p to the n minus x, and we do these calculations, and the likelihoods reflect kind of what we would assume, which is that factory A has this likelihood, factory B has a higher likelihood, and factory C, because it's symmetric, has the same likelihood as factory A, okay? But we have to combine this with the prior probabilities that, prior to opening the bag, we said factory A was most likely, and factory B and C were less likely. So we're going to kind of combine those two parts of information, and we're going to calculate the numerator by multiplying the likelihood by the prior, okay? So for class A, it's the likelihood of getting 10 if the factory proportion is 0.6, and this is kind of that binomial result that we have right here, okay? Multiplied by the prior probability that a bag comes from factory A, which we said was 0.5, okay? And we get this value. Same thing for class B, we take that binomial likelihood, or binomial probability, multiplied by the probability of 0.25, and we do the same thing for class C. And we get values like 0.05857, 0.044, 0.029, okay? And so for our for our denominator, it's going to be the probability of observing the values in x new, regardless of class label, all right? And so we've covered all three kind of possible scenarios in the universe regarding our bag, kind of given the model that we have, and it has to either come from factory A or factory B or factory C, and we figured kind of these likelihoods, right? And so the resulting probability, when we calculate them, have to add up to 1, which means the denominator is going to be the sum of these three things, okay? So I'm going to take those three parts, add them up, and make our denominator, and we get something like 0.1319. And so, so here we can calculate the probability of each of these classes by just kind of combining the numerator and our denominator. So we're going to say, so kind of just written out in words, the probability that the test case belongs to class A, given that the data that we have is 10, we get 10 red marbles out of 20, and all of our training data can be summarized with this, right? It's the probability of getting 10 red if class A has proportion 0.6, right? So this is basically the summary of our training data, multiplied by the probability of factor A, which is 0.5, divided by the probability of getting 10 red regardless of factory. So we have the numerator divided by the sum of the numerators across all classes, and we get 0.444. We do this for class B and class C, and we get 0.334 and 0.222. And I think I did all of these numbers correctly, okay? And so that's what we have. And so, 0.444 plus 0.334 and 0.222, they indeed add up to 1, okay, which is good. And so what we know is that the class label with the highest probability is class A, okay? It's got a 44% probability that came from class A, and basically only a 33 and 22% probability that came from class B or class C. Okay, so so our test case is 50% red, and if we were to base our classification on only this information, we would say it's most likely to come from B because our MLE estimate for B is 50% red, whereas factories A have 60%, factory C has 40%, okay? But with the Bayes classifier, we take into account kind of the probabilities prior to looking at the data. And specifically in our example, we're saying that because half of the bags were from A and only 1/4 came from B, prior to looking at the data, we're saying A is basically twice as probable as B. Okay, and then when we did the likelihood calculations, getting 50% red in a bag of 20 from factory A, where the proportion is 60% red, is not an unlikely occurrence, okay? So, when we combine all of this, factory A ends up being the most probable class. Right? So this is how the Bayes classifier works. We take kind of our prior information, combine it with our likelihoods, and that's going to give us basically the way we calculate the probabilities of a class label. There's a few strong assumptions that we're making, okay? One is that we tallied up the data in our training cases, and we're just assuming that these MLE estimates are the proportions of red marbles at the factory, okay? So we're just gonna assume that the factory A is using a fill proportion of 60%, factory B is using a fill proportion of 50% for red, and factory C is using a fill proportion of 40% for red, okay? So we're just kind of sticking with our MLE estimate and using that. And I think that's fine. But if you want to relax that, you can use a Bayesian approach and use that fill proportion and treat that as with a probability distribution. But that's going to be beyond the scope of this course, and we'll kind of touch upon some of these ideas in 102C, but we don't revisit this application of it. And then the other assumption that we're making is that in our training data we said that we had 24 bags and 12 of them came from factory A. Therefore, our test case, prior to looking at anything else, has a 50% probability of coming from factory A. All right, and so that assumes our sample is representative of the class proportions in the excuse me, population. Sorry. So regarding the second assumption, someone else can do something entirely different. Maybe they know that factories A, B, and C all produce equal quantities of bags, and so rather than they choose to ignore the class proportions observed in the training data and just say the prior probability is 1/3. Okay. So depending on your situation and your knowledge, that's going to affect what you do for your prior probabilities. Sorry. We're going to do the same example, just use a different kind of test outcome, and we're going to just say we open our bag, and this time only 6 of them are red. 6 out of 20 are red. So we go through, and we can do our calculations. And we say, what's the probability of getting 6 red if factory A has a fill proportion of 0.6 versus factory B has a proportion of 0.5, and factory C has a proportion of 0.4. And we do these calculations. And and the resulting probabilities are going to be something like 0.0567, 0.021, and 0.72. And so we get different results this time, okay? And so based on our data, this time, it turns out that this probability of getting, 6 red when the fill proportion is 0.6, that's kind of a very unlikely scenario. And so even though class A is more probable based prior to looking at the data, once we look at the data, it kind of makes class A very unlikely. Okay, and class C prior to looking at the data was not very probable. It was only 1 1/4 chance. After looking at our data, it's the most probable case because this is the most likely factory that's going to produce a bag where only 6 of them are red out of 20. Okay, so we're just kind of combining these bits of information to kind of get it. Okay, does that kind of make sense for as far as what the Bayes classifier is doing? Okay, I think this just sums up what I just said. Okay, so now we'll just take a look at a slightly more complicated example, and we'll do a multivariate Gaussian. Okay. So the multivariate Gaussian distribution, is this normal distribution in d dimensions, and you've got this mean vector mu, and you have this sigma matrix for the kind of the variance covariance matrix sigma. And so here I use multivariate normal, the package multivariate normal, to generate some random multivariate normal data. And so I just say, give me 30 observations from each of these 3 classes. So I'm going to call it class A, class B, and class C. And for class A, when I generate, I'm using a mean of 2 and 3. And my sigma matrix is diagonal with variance 3 and 1 and no covariance. Observations B, 0, 0, a diagonal matrix 1, 1 with no covariance. And then class C has a mean 2, negative 2, diagonal 3, 3, but some high covariance there. Okay, and then I go ahead and I just plot these, excuse me, in red, blue, and green. All right, and so this is what we get, and the idea is, you know, if you get some new observation like over here or wherever it is, which class does it belong to? Is it you know, red, blue, or green? You know, we can get some kind of probabilistic association, right? If you get something over here, it's going to be very likely to be green, and if you get something over here, it's very likely to be red. But what if it's over here, or what if it's over here, or what if it's, you know? We got to calculate these things out. I think I didn't typeset everything here. And so, you know, one thing as far as proceeding is, you know, this is a simulated case, so we know exactly the mean and this variance matrix that we used, but we got to pretend that we don't know these things, right? So as far as the means go, oh, I guess they don't fit on the slide. All we have to do is we just take our matrix XA, and we can just ask for the column means, right? And so, the column means of XA is 2.26 and 2.82. We know that the true means in the population used to generate is 2 and 3, but we're just going to go ahead and use this column mean and this column mean as kind of our MLE estimates. Okay, we do the same for class B. Okay, so our test data is all labeled, and so we're just going to take our labeled data and calculate the mean of the blue dots, and we get something a little bit different. And I guess so we get not quite 0, 0, but we get 0.3 and negative 0.1. And then lastly, for class C, the true values are 2 and negative 2, but we get 2.25 and negative 1.9. Okay, so we're getting something close, but you know, these are just it's random data, so we get something that's similar but slightly different. And these are just our maximum likelihood estimates. So all right, and then as far as the maximum likelihood estimates go for the variance, I didn't typeset the formula yet, but it's basically going to be kind of like the variance, except we're dividing by 1 over n rather than 1 over n minus 1. Okay, and so we'll do this for each class. And so this will be the resulting kind of variance covariance matrix that we get here. Okay. So I guess this I'll call variance sub A will be this, and then I'll have to calculate this for all of the other classes. Variance B and variance C. Okay, well anyway, yeah. All right, I'll fix that up. So we'll calculate the variance covariance matrix for each of these things, and then it's just an application of going all the way back to the base classifier. Here, the probability of x new given this, we're going to have some new observation, which is going to be kind of a point in 2 dimensions, and we're going to calculate the probability of getting that thing, the density. So that's going to be the multivariate normal density, all right, which is kind of this, you know, it's a little bit messy, but you know, thankfully for us, I mean, I guess I could be mean and make you calculate it by hand, but I don't think I wanted maybe just one problem, but but you can just use you know, the density, and so for univariate you would use d norm, and then for the multivariate you do dmv norm, okay, and then you give it kind of the coordinate. In this case it would be like 0, 0 if this is our test case. and then the mean will be kind of the estimate that we've estimated before, which is going to be for x bar a, it'll be this, and then the sigma is going to be kind of this variance of a that we've calculated, okay, based on our MLE estimates. And then so we get some kind of density, right? And that's going to be this part. We combine that with the prior probabilities, which probably in our case we've got 30 from A, 30 from B, and 30 from C. So this is going to just be 1/3 for all three of them. And then and we have to do this for all three possible classes to get our denominator. Okay, and then and once we do that, we can calculate kind of the resulting probabilities here. And I apologize, I didn't finish typing this up, but I'll add a few more slides here, kind of with just a couple different test cases showing the resulting probabilities that come about. Okay, and so this is so for each of these things, we're using the mean and variance matrix, which are just the maximum likelihood estimates based on the data that we have. Okay, so I think over here I've got xb and x bar b and xc. Go ahead and calculate all of these things. So we have probability for belonging to class A. This is the likelihood of coming from class B, which is much higher, and the likelihood of coming from class C is going to be this. Okay, and basically my denominator is going to be the sum of these things. Some of these values, they're all multiplied by 1/3 because yeah, so the 1/3 will all cancel out. Okay, so I'm just adding them directly. All right, but I could, technically, I'm supposed to multiply them all by 1/3 and then add them up, but they're all going to cancel out. So I'm going to just add them directly and do the denominator. Okay, and then so now I can do. For class A, we're going to do this divided by the denominator, and we get, less than 1%. We'll do this for class B and divide by the denominator, and we get like 94%. And then we'll do this for class C and divide by the denominator, and we get about 5%. Okay, so we get about 1% class A, 94% class B, and about 5% class C. Okay. And that's if we pick the point 0, 0, okay? Which kind of makes sense, right? Let's say I come over here to, I think this is like 5, 0, okay? And if I come over to 5, 0, the one that should be most likely is probably going to be class C, the green ones, and then class A, the red will probably be next most likely, and then the blue will probably be the least likely. So I, basically, I just have to, I'm going to just call this A, and we'll go to 5, 0, okay? And we'll do the same for B, and we'll call this 5 for 5, 0, and then we'll do this for C. All right. So it's nice that R has this multivariate normal density thing for calculating us, and the denominator is going to be the sum of A, B, and C. All right, and then so the probability that it comes from class A is going to be about 16. The probability that it comes from class B is very small, and the probability that it comes from class C, the green one, is around 84%, which matches our intuition when when we look at it and we put a point right here, this looks like it's going to most likely be green, okay? And it says, indeed it says this is probability of around 84% and around 16% probability that it comes from the red class, and almost a 0%, not quite 0, but very low probability that it's coming from the blue class there. Okay, so it's just an application, generalization of this to kind of multivariate Gaussian, but this is going to be the base classifier. Okay, we'll go ahead and end there for today, and we'll see you guys on Wednesday.